Okay, so we look at IIP3 and cascaded stages. So before that, let's just go back and revisit what we did last class. So we know that because of some kind of nonlinearity, your if you plot your output amplitude versus input amplitude in dB scale, you'll get some kind of compression, and the point where it falls by 1 dB is called the 1 dB compression point. Let's assume that's this. And we calculated it, right? We assumed a third order nonlinearity and we calculated your P1 dB to be root of okay, yes. No, there is no specific physical, it's just a convenient point to choose. Okay, you just need something common to describe across many different kinds of circuits. So this is probably very useful for amplifiers. Okay, however, if you're talking about maybe mixers or some other kind of circuits, this may or may not be super significant. It will be, but you may gain more knowledge from the IIP3, right? And especially we saw filters, right? We saw the case why this thing doesn't work all the time, because you could have intermodulation products. So if you have a filter, the in-band intermodulation products, you'd be able to see them, but the out-of-band intermodulation products would look artificially good. So that's why you need something called IIP3. So we looked at the what happens when you send a sum of cosines, that is two frequencies, into a nonlinear system. Okay, and we saw that you'll get a bunch of components. So you'll get omega 1 and omega 2 components, right? And those are the fundamentals, and they'll have a gain of alpha 1 plus okay, you remember this, and you also get omega 1 plus or minus omega 2, and these are the what are called IM2, the second order intermodulation. Okay, so whenever you give a sum of sinusoids, you can, okay, so to any system, right? So if you give omega 1 and omega 2 to any nonlinear system, you get p omega 1 plus or minus q omega 2, okay, where p and q are integers. Okay, depending on the level of nonlinearity you have, your p and q could be arbitrarily large. If you have a lot very high order of nonlinearity, your p and q could also be very high. In this case, we considered a third order, so we only got p plus q. So okay, p plus q is the intermodulation order. So if you have omega 1 plus or minus omega 2, p and q are both 1, so the order is 2. You also get omega 1, okay, when you have a third order nonlinearity, and these are the called the IM3 products. Now, depending on the bandwidth of your system, let's say there's a very narrow band LNA, some of these would be significant, some of these would not be significant. So for example, omega 1, let's say normally these omega 1 and omega 2 are sufficiently close, okay, and because you want to characterize the third order nonlinearity of the system. So what happens is omega 1 minus omega 2 would fall very close to DC, and omega 1 plus omega 2 would be at twice the frequency. And of course, by the way, I also forgot, you also have, of course, right? And here similarly you have 3 omega 1, 3 omega 2. These are also intermodulation products, except they are actually harmonics, so they wouldn't officially come under intermodulation products. Okay, so they actually I should be a little bit careful in my definition, because let's define it slightly different way. Let's say PQ greater than 0. Okay, if either P or Q is equal to 0, we'll call them harmonics, right? What am I doing that is? So these are the harmonics, right? So you get 2 omega 1 and so on. Okay, so and we saw that, let's say omega 1 minus omega 2 falls very close to DC. Similarly, omega 1 plus omega 2 falls close to the 2 omega 1 or 2 omega 2 and so on. And let's say the operating frequency of this is actually close to omega 1. So you're interested in the components which fall close to omega 1 or omega 2. And those are 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Is that clear? So those are the prime ones we are interested in primarily. Okay.
Why are you calling it third harmonic?
It's actually third order intermodulation. Did I say third harmonic?
It's third order.
Yes, this is the third order intermodulation.
Will measure the effect of second harmonic. Like 2 omega 1 impact of
Actually 2 omega 1 minus omega 2, you will get it only if you have a cubic term.
and that will represent how strong is my 2 omega 1.
No.
How strong is my second harmonic.
No, because if you don't even need to give us, if you give pure sinusoids at the input, right? At the output you get some components at 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Okay, they won't be a reflection of how strong your second harmonic is, right? It's why would you think that they are a function of the second harmonic? Because of the fact that you get the 2 omega? No, because okay, if you let's say if you cascade two nonlinear systems, we are going to come to that towards the end of today's class. If you cascade two nonlinear systems, okay, if the first nonlinear system produces let's say it has a square nonlinearity, it produces a 2 omega 1 component. Okay, and the second stage is also nonlinear, and so the first order intermodulation between 2 omega 1 the second order intermodulation between 2 omega 1 and omega 2 could give you a 2 omega 1 minus omega 2 component, but that will happen only if you have a cascade of stages. In a single stage where you are represented by a cubic nonlinearity, right, it comes from actually the cubed term, not necessarily from any inherent. See, you are trying to model the system as a third order nonlinearity, right? It may not have a particular like squaring term inside. You understand what I'm saying? If you have a cascade of a square and a normal a second nonlinear stage, you could get what you are describing. We will see that next class. Okay. Now, what will happen in that case? What we'll see is, because it goes to 2 omega 1. Let's assume that you are trying to cascade two stages, and each one is narrow band around omega 1 or omega 2. What happens is, if you actually get a 2 omega 1 component at the output of the first stage, it will be cut down by quite a lot. Okay, so even if it produces a third order intermod 2 omega 1 minus omega 2, that will be a lot less dominant compared to the inherent cubic nonlinearity of the system. Okay, so that is the basic thing you have to understand. Yeah. Yes. Sure, you can. The thing is, it's not about back calculating the nonlinearity. It's about some a system which artificially looks as if it's very linear. Okay, on the face of it. Okay, on the face of it, if you just take a filter, you apply this thing. Okay, so normally how would you do it? You apply an input. If the output looks very linear compared to the input, if you don't get a lot of intermodulation products, right, lot of other frequency components, you would say it is actually very linear. Okay, and if you take an amplifier, right, which doesn't cut down things outside its bandwidth, then you would get a much truer. So that kind of definition is meant to be used with amplifiers, with broadband amplifiers. If you take filters, even if it is very nonlinear, but so let's say assume it's very nonlinear, but it has a very sharp cutoff. It looks as if it's very linear, but in reality, inherently the system is nonlinear, right? So sure, you can back calculate it. Absolutely right. But we are trying to define it for systems which are, where you may not want to back calculate it that way. You want to, I guess, apply something at the input and find out what you see at the output and then calculate based on that. Okay. In a lot of cases, you may not know the. We'll look at actually both ways. Okay. We'll look at ways to calculate it based on the input output response. So you just take the input output response, back calculate things from that. So you can do that to calculate your IIP3. And you can also calculate based on applying, let's say, 2 inputs and finding out the harmonics at the output and so on. We'll look at how to calculate using both ways.
So from these two components, IIP3 components,
Yes.
how will I find out the measure of knowledge?
So, okay, the reason it's a measure of nonlinearity is you want to be able to compare. The number one reason why you want to do it is you want to be able to compare across different systems in a fair way. Okay. Second reason is, in a real case, you would be having multiple, in a very small bandwidth, you would be having multiple other. So I gave the example last week, right? If somebody is receiving a call, somebody else is transmitting something very close by, you could have a very large signal right next to it. Okay. So you want to be able to characterize such a situation. Okay. So that's the reason why you want to do it in terms of IIP3 specifically. IP3 specifically. Okay. Now, once you use IP3 to characterize different nonlinearities, then you can, what we'll see is there is a relationship, for example, between 1 dB compression point and IIP3. Okay. So you can actually, compare across systems, even if you know only the 1 dB compression point or the IIP3. Okay. Okay, so let's go back and look at the different terms coming out of it, right? So let's assume the input output response is alpha naught plus alpha 1 x of t plus alpha 2 x square of t plus alpha 3 x cubed of t. And we'll also assume that, all of these are, so this is called actually that is not a bad way of representing it, of course, because now you have a DC offset, right? But we assume that you have some kind of soft nonlinearity, that is, you don't have non-monotonicity and so on, right? You just have some kind of compressive effects. Okay, and let's assume that x of t is, okay, so one of the first things you do is when you're measuring IP3, so in a real case your interferer could be much higher than your desired signal. Okay, but when you measure it in the lab, you want to have a standard way of measuring it across many systems. So what you do is you give 2 tones at the same amplitude, with the same amplitude. Okay, so we'll assume it's a cos omega 1t plus a cos omega 2t. Okay, and we'll assume that omega 1 and omega 2 are nearly equal. So let's look at the components of y of t. So first of all, you have DC components. What do you have? DC components is of course alpha naught. Okay, and we saw last week, right? Even orders will also give DC components. So in this case, because we have just taken a second order system, you'll get a DC component from the second harmonic term. Because you'll get a cos squared and you write it as 1 plus cos 2, right? Cos 2 omega. So you'll get a DC term from that. Okay, and this is of course the output bias, and this is your offset. And the larger your, the more number of terms, even order terms you consider, the larger the offset. Okay, the more accurate actually, because the extra offset added by those larger terms will also fall. Okay, how about the fundamental? So we saw that you have alpha 1 plus times okay, and this is your desired gain term alpha 1, right? Ideally you want only alpha 1, and this is your third order intermodulation product, and that will give you sorry, not your third order, it's not your intermodulation product, it's your compression or expansion depending on the sign or sign of alpha 3, okay. So this is your compression.
So if some amplifier has a characteristic where it is expanding,
Okay.
and it is coming back.
Okay.
So in that case, we will take expanding 1 dB term as a criterion.
So normally if you had such an if you want to design such an amplifier, the reason you would want to design a gain expansion kind of I guess circuit is because you want to extend out your 1 dB compression point, okay. So what you'll get is you'll get I think we showed this last week, so you'll get a term like this, sorry, your input output will look like this. So let's say not output power versus input power, right? I think last time we looked at, so no, it just compresses normally like this, and so you might get something like this, right? It will still compress, but maybe at a higher power, okay.
So my point is here, should we take the expanding 1 dB point as a
No, it will still be the compressive 1 dB point, okay. You will still take the compressive 1 dB point. Now the thing is, the way you would get gain expansion is one of those ways is by making alpha 3 as positive, okay. Now what that also means is you may also get actually you may be adding other nonlinearities to make it actually worse as far as maybe the IIP3 or something else is concerned. Even though your 1 dB compression point may look slightly better, and your IIP3 may also look slightly better, but there may be other harmonics which may look much worse, okay. Now the other thing you can do is you can try to do something like this. You can try to cascade two amplifiers. One has gain expansion, other has gain compression. You can try to do something like that, okay, to extend out your overall P1 dB, okay. But you have to be careful because so far if you see we have actually been looking at just the magnitude of your output. You will get phase distortion, okay, and eventually what you see is phase distortion will end up affecting your nonlinearity a lot more, okay, if you do something like this.
But in general, we never operate the amplifiers near the 1 dB,
Yes,
particularly in the modern computer.
yes. So if you take LNAs or systems like that, you probably will never operate it near the 1 dB compression point. Yes, yes. Now the spectral degrowth could be due to phase or amplitude distortion. Now you may take care of amplitude, but phase so it would happen, for example, in a transmitter in a PA where you could be operating in very high compression.
But there also look for the
So the thing is, so what happens is you will be using it in such a case when you are trying to cut down something, right? Of course, if you take a standard off the shelf gallium arsenide device, you may not be able to do it. But let's say you want to push the envelope and design the same amplifier in a different, let's say in CMOS, where in general it compresses at a much lower power, but you want to compress it at a higher power, then you would want to push the envelope and do something like this, okay. And when you do that, you will be operating actually what was originally the compressive region of the amplifier, and you would see effects, okay, phase and amplitude distortion effects, okay. So let's look at the harmonic terms. So for the second harmonic, okay, actually alpha 2A, actually let's just do it this way. The third harmonic is alpha 3 A cube by 4 times okay, and as we just discussed, these are pretty far out in compared to your operating frequency, they're usually attenuated, so you're not interested in these terms anyways. So then let's look at IM2. So IM2 happens to be proportional to alpha to a squared. So you get cos of omega 1 plus omega 2 and cos of omega 1 minus omega 2. Now, of course, one thing to see is it's proportional to a squared, the amplitude, and the other thing is the cos of omega 1 minus omega 2 term, it actually falls close to DC. Okay, if you take the system which we considered last time where you have an IF frequency, it's not a problem, but we'll see later in the course there are what are called last week we called it a heterodyne receiver. Okay, super heterodyne receiver. There are also what are called homodyne receivers or direct conversion receivers. Okay, in these receivers you are directly converting the signal from RF to baseband. In that case, if you have any omega 1 minus omega 2 term, it could fall right on top of your signal and it could be a problem. So what you'll see is, if you have super heterodyne systems, IIP3 and IM3 products are very important, but if you have a direct conversion system, IIP2 terms are very important. Okay. Okay, so you have so I'm just putting it as plus or minus, but you basically have 4 terms. And again the same thing holds, 2 omega 1 plus omega 2 and 2 omega 2 plus omega 1 are much closer to 3 omega. So they probably get attenuated a lot more. Okay, so let's take an example. So let's look at a normalized case where let's say omega 1 is let's consider just normalized frequencies, right? So omega 1 is 10 and omega 2 is 11. So the components you'll get at the output are, so you'll get the fundamental gain terms 10 and 11. Okay, then you'll get the second, actually let me draw it a little bit better. Okay, then what do you get? 2 omega, what is 2 omega 1 minus omega 2? It's 20 minus 11, which is 9. Okay, so you get a 9 term. And what is 2 into omega 2 minus omega 1, which is 12. Okay, what is omega 1 minus omega 2 minus omega 1, which is 1. So draw the x-axis, so you get something at 1. Omega 1 plus omega 2, you get something at 21. Okay, then you get 3 omega 1 term, which is 30. Okay, so 2 omega 1 plus omega 2, which is 31. You get a 32. 2 omega 2 plus omega 1 and 33, which is 3 omega 2. So it looks something like this. So you'll get a bunch of products, right? It won't look clean anymore. Okay, so now we have so far been talking of IM3. Okay, so we'll define what is called IIP3, which is called the input referred intermodulation product, third order intermodulation product. Okay, so how do you calculate this? So what we'll do is, it's defined as the extrapolated power where the power of the fundamental becomes equal to the power of the third order intermodulation product. Okay, so let's try to plot it on a log plot. Okay, So let's say the first order, remember that it has a slope of 1, right? The first order has a slope of 1, and remember that the third order is rising at a cubed, right? Have a slope of 3. Okay, now in reality this will compress, and similarly what you will see is, because of higher order nonlinearities, you will actually see compression even in the third order. Okay, because you will have even higher order terms, odd terms coming down on top of your third order. Okay, so if you extrapolate these as a straight line, you get a point which is called the, so this is called the IIP3, and this is called the output referred intermodulation product. Okay, right? So those are the two curves we are plotting. So alpha 1a was the gain, right, of the fundamental. Okay, so and remember the definition of IIP3 requires you to use equal amplitudes, okay, and two tones. It's called, quite often you'll find people calling it a two-tone test. So they'll ask you, have you performed the two-tone test on the LNA, right? Because you're giving two equal tones. Okay, let's try to find an expression for IIP3. So
IIP3 plot means log of the bracket being everything in the log and plot generator. Log of bracket alpha 3 is a.
So since it's proportional to a cubed, it's going to have a slope of 3, right? And since it's proportional to 20, alpha 1a, so what you are varying is actually a. Okay, so that's why this has a slope of 1 and this has a slope of 3. So what you're going to do is, you're going to vary input amplitude, and if you vary input amplitude, if you plot the first harmonic fundamental, it will have a straight line at low powers, because at low powers your nonlinear effects don't come into play. Okay, and similarly at low powers, you know that 3/4 alpha 3a cubed has a certain slope of 3, and you can do it. Now in a real case, you would actually compress a lot before you reach your IIP3. You can never really apply an IIP3 and find out if those two things are equal. What you do is, you would choose 2 points, okay, and then extrapolate it. You would choose 2 points on this and extrapolate that. The meeting point is IIP3. The meeting point, the input power is IIP3, output power is OIP3.
This even for alpha 3 cube, that is a term related to first harmonic fundamental itself.
No, it's actually the third harmonic. This guy. Yeah. Okay. Okay, so it's quite easy to calculate it, right? So the power, let's say the power is AIP3. So obviously, since the two things are equal, the gain here is alpha 1 times AIP3 is because you know you're going to extrapolate it and make it equal. So what you're okay. So what you'll see is your IIP3 is actually going to be a function of alpha 1 and alpha 3. So your first and third order cubic nonlinear. Okay, alpha 3 is a cubic nonlinearity. Alpha 1 is your fundamental gain. So once you relate to that, this is a common test you can apply to multiple systems, even if you don't know alpha 1 and alpha 3. Okay, you can apply certain powers. Okay, without characterizing system itself, you can apply 2 powers, find out what harmonics you get at the output, and plot this, and compare across multiple systems.
Basically, the magnitude of that IIP3 is a measure of the.
Exactly. So the magnitude of IIP3 will give you a measure of how nonlinear your system is.
Since we are we take the non-linear region and do some.
Okay.
For that, I can.
Take a case of a perfectly linear system. Y of t is alpha 1 x of t. This curve looks like this. This curve, actually it's minus infinity. So your IIP3 is infinite. Okay. So depending on how large your 2 omega 2 minus omega 1 and 2 omega 1 minus omega 2 amplitudes are, the point where they meet will change. Okay. Point where they meet will change. 4/3. Okay. Yes. Yes. But what this allows us, if you put it in this way, what we are going to see is, remember that we know that your 1 dB compression point is also related to alpha 1 and alpha 3. So you can actually relate these two. Okay, we'll come to that. Okay, so it is a way of, the reason we are putting it in terms of alpha 1 and alpha 3 is because we are going to, what we are going to do is, we are going to use this relation to try to find out what tests we can do on the system. Yes.
In my case, only third harmonic is dominating.
Okay.
Can I directly find the SNDR using this curve?
Yes. Yes, you can.
Spacing will be just the SNDR.
Yes. That's right. Okay. So the other thing is, of course, if you want to define it in terms of power, so you need to refer it to an impedance, right? Now we are just talking about amplitudes. You need to refer it to an impedance. Source resistance RS. Okay. Now the other relation we know is, what was P1 dB? It was root of, actually that was A1 dB, right? Is this right? 0.145 alpha 1 or alpha 3, right? Is it 4/3 or 3/4? 4/3. Okay. So what you'll get is your, I think it differs by approximately 9.6 dB. And of course, same thing for P1 dB, right? Okay, so this is one relation. So we managed to relate your P1 dB to your IIP3. Okay, so now let's see how you can measure IIP3. So let's see if we can actually measure it using actually a single tone. Okay, so let's say your input power is actually AN. So what is your output power at?
This relation is applicable only when higher order harmonics are not.
Exactly. So that is one thing you should always remember. We have so far in calculating this relationship between P1 dB and IIP3, we have assumed just a cubic nonlinearity. In reality, if your compression is caused by higher order nonlinearities, then this relation is no longer true. And in the real case, you would probably not have such a nice relationship across all systems.
But still the point will be measured from it. Doesn't matter how many terms.
Yes, that's right.
lot of products which are
Yes,
actually due to
that is due to higher order. We have assumed a cubic. If you assume a cubic, you'll never get a bend. You'll keep going. But in reality, if you take a real system, you can never represent it just by a cubic. You will usually have a fifth order, seventh order, and so on. Those will cause so just like your higher orders cause compression in your first order, even higher orders will cause compression in your third order characteristic. Okay, so that will cause your IM3 curve also to compress.
in the previous speech. Sir, there
Yeah.
should be a relation of log between that.
Why?
Square and one is
No. This one is also square, actually. So this is root of 4/3 alpha 1 over alpha 3. The other one was root of 0.145 alpha 1 over alpha 3. So the relationship is root of 0.145 over root of 4/3.
when you take dv in both the sides,
Okay.
so in this case you will have half log 0.145 by 4 by 3.
And you'll get a half log.
No, when you take the power, a square.
Okay. Yeah, sure, you'll get a power, but if you calculate it, it'll come out to 9.6 dB. Okay. So what is the power at? So let's call it a omega 1 omega 2. So we don't know that power yet, but that's what you're going to measure. And so let's say your IM3 amplitude is a IM3. So theoretically, what do we know about this? A of omega 1 omega 2 is the power should be alpha 1 times AN. Okay. So remember, when you measure IIP3, usually you give very small signals. You don't want to move into the compression region. Okay. So when you design your LNA or something in the lab, in your simulation, the point where you choose, so if you end up choosing a point where it's already started compressing, you will get a different value of IIP3. Okay, so just make sure, be judicious in your choice.
Related to the square of them.
Which power?
What is P of W?
Yeah, the power, output power.
So, and what is A?
A is the amplitude. But now, okay, so let's do it this way. So let's just call it this. You're right, good point. Because we are talking about amplitudes, we should compare amplitudes. Okay, so what is this? Okay, so if what you do is you give a certain input amplitude, you're going to measure the fundamental gain. Okay, you're going to measure the power, the amplitude of the intermodulation product. Okay, so you have a clear relation between AIP3 and I mean you have a clear expression for AIP3. So this is a easy way of measuring AIP3 using just a single power. You don't have to take, if you want to extrapolate, draw the graph, you have to take measure at 2 powers. This may be an easy way to measure it using single powers. Okay. Okay. So let's see what else can we do. So let's see. Let's just take 20 log on both sides. Oops. So you're going to divide by half on all sides. Is this clear? You're just taking 20 log on all sides, on both sides. Okay. In fact, what effectively you're doing is taking a root, square root on both sides, and then taking 20 log. Okay. So what does this mean? So let's say at the output. Okay. So you get this. These are omega 1 and omega 2. Okay. These are your IM3 products. What is the power difference between them? Nothing but this, right? 20 log A omega 1 omega 2 minus 20 log A IM3 is the delta P. Okay, this is a very simple relation in terms of power quantities. Okay. Obviously, if you want to go to power, you would take RS, right? Refer it to a resistance on all sides, but it's understood. Okay. So let's see one more method to calculate this. It's called the 3-point method. So what we're going to do is, so let's assume your nonlinearity is something like this. Okay. What we're going to do is, we're going to find the slopes at 3 points, at the negative extreme, around 0, and at the positive extreme, and relate that to IIP3. So let's say in this case, let's take a case of, let's say you're designing with a MOSFET. So this is your current versus voltage curve. Okay. So I of VDC plus your signal is, let's say, some C0 plus C1V plus C2V squared plus, so you have some, okay. So this is effectively, it's a measure of GM, right? C1 is a measure of GM. Okay. What is G of 0? It's your slope. So we're going to define G of V is, so what is G of 0? C1, right? First of all, actually, what is G of V in general? It is C1 plus 3C3 V squared. Okay, that is G of V in general. G of 0 happens to be C1. So let's say these are the 2 points we are calculating at, right? Minus V and plus V. Okay, so you're measuring it at the positive extreme. And the negative extreme. So what is negative extreme? Of course, gives you minus. Okay. Sorry. This is the signal actually. So you are allowed to give it. Obviously, okay. So let me say this is the I versus V signal, not DC. Okay. So I should be, you're right. So let's just call it this way. Okay. In the real CMOS case, like he said, you only have a positive rail, right? But this is a general method which could be used for example, for a bipolar case. Maybe you have negative rails, right? So it doesn't matter. Okay. Now, with these three curves, right? With these three equations, obviously you already know C1 in terms of G of 0. What you are measuring is G of V, right? At these 3 points. So you already know G of 0 is C1. Using these two, you can calculate C3 and C2 in terms of G of plus V and G of minus V. Okay, so you can calculate, of course, C1 is G of 0. C2 happens to be by 4. Okay, is that clear? So you got it in terms of V. Now what do you know about your IIP3? You already know if you have something like this, your IIP3 is 4/3, in our previous case we used alpha, in this case I use C because you're doing current versus voltage, but yeah, you know it's 4/3 alpha 1 over alpha 3. Okay, so it's 4/3 C1 over C3. Actually, let's calculate the power directly. 2/3 so this happens to be 4V squared over RS times G of 0 over okay, so let's stop here. I think next week we'll continue with cascaded stages. Okay, so what happens to the IIP3 of a cascade? So if you have one block with an IIP3, certain IIP3 1, second block with an IIP3 2, what happens, and certain gains, what happens when you cascade them? So we'll look at it next class. IIP3 is always power. Okay, AIP3 would be amplitude. Okay, IIP3 is always in terms of power quantities.